A very good afternoon to all. My name is Gopendra Kumar, lecturer of Department of Electrical Engineering, IIMT College of Polytechnic, that is in Noida. Today I am going to discuss the impacts of various electric vehicle loads, that is EV load, which is connected with grids. These days, EV greatly impacts the grids because of its charging and discharging processes, which consumes electricity, and its surplus may also supply the electricity. Uh, Introduction is that with the rising concern about greenhouse effects, emissions, clean and sustainable energy uses is becoming increasingly common. Electric vehicles have grown in popularity in recent years as a result of their environmentally friendly design. Government also take incentives policies posing significant grid challenges because environment concern is very much important these days. People's trying to reduce the carbon footprints. That's why we are moving ahead towards the renewable energy and try to reduce our dependency on petrol and diesel, that is conventional sources of energy, which also creates pollution that is not eco-friendly for us. As compared to conventional power loads, EV charging EVs has unique characteristics. Creations of modern power grid that is focused on practical, errorless modeling of electric vehicle power consumption management, and a study of electric vehicle charging influences is necessarily required. Several attempts are made to increase electricity output by harnessing energy from renewable sources such as solar, wind, hydro, geothermal, nuclear, and others. At different stages, these sources are used separately to produce electricity. The most difficult task is to transfer the energy that is produced on. This transfer is difficult. That's why some steps are we are trying to take some steps. Scientists are also doing work in this field. The PV panels, wind turbines, and diesel generators provide enough power to the microgrid to meet the needs of micro customers, that is, small consumers, grids at all the time. Here we have modeling of single and multiple electric vehicle loads. Here we have model. We have broadly 4 blocks. That is modeling of that DC side, which is fed by battery parameters. That is initial current, voltage, state of charge. That is fed to modeling AC side, that is power AC, current AC, which is connected to EV chargers. That block constitutes modeling of single electric vehicle loads. Next one, that is aggregate of this is fed to the initial state of charge distribution, which output is taken as an input for start charging time and quantities, which results power to electric vehicles. That last 2 blocks, initial state of charging distribution and start charging time and quantities, constitutes modeling of multiple electric vehicle loads. For better understanding, these modeling of single electric vehicle loads, the modeling of DC side loads, and modeling of AC side loads. And in case of modeling of aggregate electric vehicle loads, we have a state of charge distribution model at the start, at the beginning, and next time to start charging model. This is the proposed model of work. Here we have main grid, secondary load, EV loads, microgrids. These all are connected, and that is our motto. First of all, our microgrid is connected to main grid through power coupling, PCC, and with the help of feeder, secondary load are fed, and other power system network are also supplied from that feeder. And our microgrid is also connected to EV loads through a large battery system, generators, wind farm, PV panels, which indicates when we have when electric vehicles require energy, then that grid supply a renewable source of energy that is generated from wind farm, PV panels, and other sources in order to charge the EV battery, EV loads. If in case of cloudy weather, and when wind is not appropriate, then this source of energy, we can't get this source of energy. That in that case, with our electric vehicle, which needs charging, it takes energy from main grid that is connected to a microgrid. If our EV has sufficient charges, that is fully charged, and we don't require as much energy that is charged, then in case of need, it may also supply energy to the grid. That is the benefits of EV loads. It's behaved as it's also support our power system network. This is the proposed Simulink model of the system, in which several EV loads are connected. When people are going to the market, when they are going to the jobs. In case of evening, when people are going back from home from their duties, most of the vehicles are connected to the loads. Then its impacts very high to the electrical system. They are consuming as much energy. In case in evening, we have lighter load. In morning we have lighter load. In afternoon we have little much loads. So we have various patterns of EV loads that is connected across the grids. That shows the behaviors of grid that is changing, that we have shown in the result in later case. Here we have Simulink model that is connected with diesel generator of 7.5 megawatt, which is also connected to the wind farm and solar panels that is also generating energy. Renewable sources are also connected to the main grid, and which is also supported by diesel generator DC. And vehicles are connected, electric vehicles are connected as a load, that is when it supply energy to the vehicle, that is vehicle to grid. When it is connected, when it supply energy to electric vehicle, that is grid to vehicle, G2V. When our vehicle supply energy, when it is sufficiently charged and system required energy, then our vehicle, which is fully charged, having sufficient energy, they also supply energy in that case. So that kinds of the transfer of energy is bidirectional. That is vehicle to grid, that is of 4 megawatt, 100 into 40 kilowatts. Scopes, here we have the blocks of scopes that shows the different parameters on the screen. Power measurements units measures the power of measurement system. We have also connected transformers. As per the need of power, they step up and step down the power as per requirements. The various parameters, the blocks that are connected having following parameters, which is listed here. The component name diesel generator, that is of 7.6 megawatt. Transformer, that is 25 upon 25 kilovolt. Transformer 2, 25 kV upon 600 volt. Bus bar 1, bus bar 2, PV farm, that is of 4 megawatt. wind farm that is of 2.5 megawatt, EV load that is of 4 megawatt, frequency that is 60 hertz, and grid supply that is 320 AC. Here we have supply AC system. Here we have the results of various loads that is connected across the grid. This is the load profile of EV load 1 connected to microgrid. Here in vertical axis we have shown power, and horizontal axis the time is indicated. The regulation data when load is connected. The green line shows regulation data 1:1. Blue line indicates regulation data that is 1:2, and the red line shows the regulation data 1:3. Next showing is graph showing charging data when load 1 is connected. This shows the charge, how charge varies, how it impacts. Its variation is shown. That is almost linear. Or in same fashion, we have on vertical axis charge is indicated. On horizontal, the time is indicated. On the scale of 10 into 4, 10 raised to the power 4. Red line indicates the charge data 1:3. Blue line indicates charge data 1:2, and the yellow line charge data 1:1. Here we have states of charge when load 1 is connected. The ion concentration is indicated on vertical axis, and on horizontal axis time is indicated, that is on the scale of 10 raised to the power 4. For certain time duration, our graph is linear, and after that it suddenly falls, but it doesn't reach the negative points. It reaches the zero value. Then after maintaining zero for certain period of time, it suddenly rises on the vertical axis. Then the pattern of graph changes slowly but gradually. It rises in both vertical and horizontal axis. Then again it's become constant for certain period of time, and it's maintained the peak value. Then again it's decreases abruptly, and it reaches the minimum zero value, and the graph is repeating same. That means here the state of charge for load 1 is same. It's repeating its nature. Now we are discussing the power consumption for regulation data when load 2 is connected. The yellow line indicates the regulation data 2:1. Blue lines regulation data 2:2. Red line regulation data 2:3. There are some spikes arises due to sudden charging and discharging when some electric vehicle suddenly connected to the grids. Thousands of electric vehicles connected to the grids, and it draws more power. If suddenly withdraws, if suddenly we disconnect the electric vehicle, thousands across the country, thousands, 10,000s of electric vehicle in certain period of time we disconnected, then its graphs fall in the next case. So here spikes arises. In second case, in case of charging status, when charging data when load 2 is connected, we see the spikes that exist for some period of time. Here in the above data, we are seeing it's behave like spikes, but here it exists for a certain period of time. That is also very lesser. Between 1 and 2 seconds, it shows minor spikes that is exist for some period of time. In case of charging, parameters are same. Yellow indicates data 2:1, blue indicates data 2:2, red indicates data 2:3. So we can see the patterns, how it works as per our connection, disconnections, charging profiles, and this shows state of charge. Here also we have ion concentration on vertical axis and time on horizontal. At first, when battery is charged, the ion concentration is fixed, that is constant. After certain value, it suddenly discharges and it reaches to zero value, and it maintain its value, and after some time it again suddenly abruptly rise to some value that is more than 50 that we have taken the value, and then it slowly increases in both horizontal and vertical axis, and then again becoming constant at this region that the previous value existed, and again graph is doing same thing. That means here also the charging profile, the concentration of ion concentration is same in both case of charging. What we have concluded, the result of various electric vehicles load connected with the microgrids are shown before. The genetic profile belongs to three types of electric vehicles with different types of consumptions profiles based on activities of electric vehicles user. Load 1, load 2, and load 3 signifies the electric vehicles load 1, 2, and 3. All three loads behaves in different manners and have different impacts on power regulation, charging from grid. The profile of load 1 is when EV is charged by the owners when they are at office and working. We are already discussed. These are the profiles of charging and discharging in different instant of time, different durations of time for different time periods. That is indicated here. The profile 2 of the load is when EV is charged by the owners when they are at office working but have to drive far and come back to the office next day in a one single charge. Okay. The profile of load 3 is when EV is not charged by the owners when they are at office but is charged at home at any time of the day during 24 hours. The variations in the profile is depend on the duration of charge, duration of charge, duration of discharge of battery due to the ride, possibility of ride back for longer distances, and during no obligations on charging, and the vehicles when at home. We have concluded that in this research, the simulation are run for 24 hours. 5 different electric vehicle loads are connected to hybrid microgrid. Individual, such as electric vehicle loads, connected once at each time in 24 hours time frame. Because if we connect simultaneously, then we can't analyze the things. That's why we are individually connects the load at once at a time in 24-hour time frame. Due to the load variation, the grid parameter, state of charge of vehicle batteries, charges are observed, and microgrid performs better when electric vehicles load connected at off-peak hours. Microgrid perform worst when electric vehicle connected at peak hours, that is shown in the graph. Performance of microgrid observed average when electric vehicle loads are connected other than peak and off-peak hours. At the point of charging, electric cars have an effect on power utility grid. Controlled charging of electric cars has significant impact on grid's efficiency, that is few of the parameters like power factor, voltage of the link grid. The negative impact of electric vehicle on electrical grid can be reduced along well managed bidirectional charging. Electrical car charging, that is time to severe the grid as a micro generator during peak hours and as a load during off-peak hours is extremely beneficial to the power grid or microgrid. That was the overall conclusion of electric vehicle that is connected to our grid and its impacts. When LEV are connected to the grid, then the behavior of the grid is changing because of its impact. It suddenly withdraws power. When we uh, disconnect our vehicle from charging, then uh, it reduces the impact on grid because grid have to less supply the power. So it has different profile. Some person connects their electric vehicle in different hours, some connects in different hours. So grid behaviors badly changes, adversely changes. So with the help of this analyzing result, we can improve the performance of grid. That's why their analysis and their need to study the impact of grid behavior is important. Thank you.